So now that we know a little bit more about these nuclei, you can think about some of the things that happen with nuclei. One thing is what we call radioactivity, which is the spontaneous emission of radiation. So it's essentially the random change that can happen in the nucleus, in an unstable nucleus, and that change will adjust the nucleon, so like a neutron can turn into a proton, and you'll emit some stuff from the nucleus. That's radioactivity, that's radiation coming out of that nucleus. And as it turns out, radioactive decays occur for, I think the book says, all proton number greater than 82. So 82 protons is lead, so greater than lead on the periodic table. Decays happen for all those elements. And then, of course, like we saw, there are some unstable isotopes of elements with lower atomic numbers, so decays will naturally happen with those as well. So when you're talking about decays, this goes beyond just thinking about nuclear physics. The general process of decay happens in many different areas, but the fundamental property of decay is that you have this change of the number of things, and that thing, that rate of decay, the change of number of things, is proportional to the amount of things there. So we can write that as a differential equation. Minus dN dt, the rate of decay, is equal to some constant, called lambda, multiplied by the number of things there. Right now we're talking about a nuclei. And you can get to the solution to this equation in a couple of different ways. The book shows you how to do it. Here, just to point out that this equation is saying that the slope of something is equal to a constant times itself, meaning that you take a derivative of something and you get the same thing back plus a constant. The only thing that does that is the exponential function, e. So you can kind of see why this differential equation ends up giving you this decaying exponential. Lambda we call the decay constant, and you can write 1 over lambda is the lifetime, and there's a lifetime, sometimes written as tau. And you can quantify the decay of things in different ways. One very widely used one is having to do with the half-life. The half-life is the amount of time for half of the material to decay. So if you start out with a kilogram of radioactive material, in one half-life, you'll be left with half a kilogram of that material. The rest of it, you might still have the same chunk there, but it's actually not the same material anymore. Half of it is decayed and becomes something else. It's pretty easy to relate the half-life, the T1/2, to the decay constant. So the decay constant comes directly from the differential equation. But if we want to think about the half-life, or the time for half the material to decay, we can find that in terms of that decay constant. We're just saying that the number of nuclei left out over one half-life is going to be whatever amount we started with over 2. That's all we're saying with the half-life. So if we put that into the equation we got for decay, then the time, right, is 1 half-life. These guys go away, and take the natural log. That's 2. Take the natural log to undo this exponential, because we end up with minus that. So we can write the decay as minus the natural log of 1/2 over the half-life. Turns out that minus natural log of 1/2 is 0.693. So that's how we get that relationship there. And if you plot this relation, well, no surprise, it just looks like an exponential, decaying exponential. So if you start out with n0 amount, in 1 half-life's time, you'll have dropped to n over 2, half that amount. In a second half-life's time, you'll have dropped another half, or half of 1/2, just to 1/4. So we're talking about radioactivity. You can just call the activity of that radioactive material A. A is the rate of decays of that material. So A just equals that minus dN dt, and if you put n, the function for number of nuclei remaining after time t, you put that back into the derivative, then you just get a minus and lambda out. So the minus cancel, you just have lambda n. Plug in the functional form of n again, you get this. And we can write the activity as a function of time as just another decaying exponential, and a0 is just lambda times the n0, the initial amount of nuclei. So the unit for activity is a becquerel, I don't know how to say that, BQ, and it's just 1 decay per second. Another common unit named the Curie has to do with the radioactivity of radon, I believe, but it's basically just a scaled becquerel. It's 3.7 times 10 to the 10th decays per second. And if you plot the activity as a function of time, no surprise, it just looks like decay rate. It's the same basic decaying exponential. Nicely enough, though, if you are able to measure the activity of a material, how many decays per second, then you can pretty easily get the decay constant for that material, where you sort of linearize this activity by taking the natural log of both sides, using the natural log properties to split up that natural log. If you plot y as the natural log of the activity, you end up with this linear relationship where the slope is minus the decay constant. That's a nice way of finding the decay constant. You can do another example, but we need a little bit of background maybe on one of the uses of radioactivity, which is dating materials based on the amount of a radioactive isotope that's in that material. So one form of this radioactive dating is called radiocarbon dating, because you use an isotope of carbon, namely carbon-14. Carbon-14 is an unstable isotope, but its half-life is like 5,000 or 6,000 years, so it's a pretty long half-life, so it sticks around for a while. So the basic idea behind radiocarbon dating is that carbon-14 is created generally in the atmosphere of the Earth by collisions from stuff coming from outer space with nitrogen in the atmosphere. You end up creating carbon-14. That carbon-14 ends up, combining usually with oxygen in the upper atmosphere and sort of drifting down into the lower atmosphere. And as far as chemistry is concerned, carbon-14 is exactly the same as carbon-12. Remember, molecules, the bonds, the chemistry, that all was determined by the electrons and electron configuration, and largely just by the valence electrons, really. So carbon-14 gets incorporated into the life cycles of organisms just like carbon-12 would, just like normal carbon. Particularly with photosynthesis, where plants take in carbon dioxide and use that to create energy for themselves. But yeah, so carbon-14 enters the food chain through this photosynthesis process, and then animals will eat it, we'll eat animals, right? The carbon-14 gets incorporated into all these living organisms through this food chain. So the thing is, while an organism is living, they keep sort of uptaking more carbon, and they keep replenishing the carbon-14. So while they're living, carbon-14 is being taken in, it's decaying, but you keep replenishing that with more. So in a living organism, the ratio of carbon-12 to carbon-14 is pretty much constant throughout their lifetime. However, once the organism dies, it no longer replenishes carbon, and so the carbon-12 it has stays the same, it's stable. Carbon-14, though, is going to keep decaying, and since it's not being replenished, it's going to slowly decay away. Eventually, you're going to end up with no more carbon-14, long after that organism has died. So basically, knowing the ratio, or measuring the ratio of carbon-12 to carbon-14 in organisms, deceased organisms, allows you to date when that organism died. It's a very useful technique. And actually pretty easy to implement, at least once you've measured the carbon-14. So in this example, you say that you're an archaeologist and you found some ancient wooden furniture, and only 80% of the original carbon-14 remains in that wood. How old is that furniture? Okay, so we go back to our decay equation. And they're saying that after a certain amount of time, we're left with 80% of the original amount. So if I have the current amount and I divide it by the original amount, 0.8, 80%. That's what we're told here. So that means just divide all this by n0, that 0.8 should be equal to minus e, or e to the minus lambda t. So we just natural log everything. That's saying that the time looks like minus the natural log 0.8 over lambda. And we actually know the half-life of carbon-14 is 5,730 years. So let's write the decay constant in terms of the half-life instead. Uh, 693 over that, or this times that half-life, 5,730 years. Put those numbers in, you get 1,844 years. Pretty old piece of furniture. Okay, so we're talking about radiation. What kinds of radiation are there? It's like they're not just one kind of radiation. There are multiple ones. The main sort of categories of them are alpha, beta, and gamma. So if you know anything about the Greek alphabet, you might know that people were just lettering them without really knowing what they were. They're like, oh, there's the first one, there's the second one, there's the third one. Alpha, beta, and gamma. And we'll talk about what they are in a second, but one important thing to know about these different kinds of radiation is their penetration. How deeply they'll go into materials or what they'll pass through, because that indicates how you can stop them and also maybe how dangerous they are overall. Alpha radiation, very little penetration. For beta radiation, it'll go through that paper but won't really go through metal. Gamma radiation can go through most things but doesn't really pass through lead very easily. So when they were first discovered, they were thought of as rays. We call them alpha rays, beta rays, gamma rays. But what are those actual rays made of? So it took a good amount of effort in order to figure out what these rays were actually made of or composed of. One way of getting at what is like an alpha ray, or a beta ray, or gamma ray, is creating these rays or having radioactive sources that produce them and allowing those rays to pass through a magnetic field. If these rays are made up of electrically charged things, then the magnetic field is going to curve them based on their charge. And in fact, also the amount of curvature is related to the momentum or the velocity of those particles as well. So just this one experiment, you can sort of get at, well, what the charge is, if it is charged, and possibly getting at what the mass is, or at least the charge to mass ratio. So use your right-hand rule for a Lorentz force, charged particle moving through this magnetic field. You'll see that the alpha ray was positively charged, the beta ray, or at least the standard beta ray, negatively charged. Gamma ray wasn't charged at all. This and other sorts of experiments eventually put together that alpha rays, or alpha radiation, is made up of helium nuclei. So that's just standard helium nuclei, 2 protons, 2 neutrons, all the electrons stripped away, or doubly ionized helium. Beta radiation turned out to be electrons. That's it, just one electron. Or an anti-electron. So we call those positrons, and they're the same as electrons, except they have a positive charge. It's a negative charge. And then finally, gamma rays were found eventually to be high-energy photons. Probably already knew that one. We talked about gamma radiation, or at least the gamma portion of the electromagnetic spectrum. Let's look a little bit more at these kinds of decays, or the things that produce those different kinds of radiation. Alpha rays, beta rays, gamma rays. First, the alpha rays are produced by alpha decay, and that happens when basically a chunk of a nucleus gets pushed off in some way. We're not too concerned with how it actually happens, just the fact that this is what goes on. So you start out with, say, a uranium nucleus, and 2 protons and 2 neutrons get pushed out of it in whatever way. Right? So that 2 protons, 2 neutrons, that's the alpha particle. So that's what we call the alpha ray. The thing that's left over is something with 2 less protons and 2 less neutrons, thorium. And this is just an example of an alpha decay. There are plenty of other elements that go through alpha decay. So when you're talking about decays, you often talk about the parent nucleus as like the beginning thing, and then the daughter nucleus is the thing that ends up with. And we can write it symbolically as our element with an atomic number and atomic mass number becomes a new element with atomic mass number that's 4 less, because it lost 4 of these atomic mass units here, and its atomic number is 2 less, because it lost 2 protons. That plus the helium nucleus. So for beta decay, remember, beta rays can actually be electrons or anti-electrons, positively charged electrons. So this is an example of a beta decay with an electron, and in that case, what you end up with is actually a neutron getting transformed into a proton, and you get an electron shooting out of it, or shooting out of that nucleus. Again, this is just an example of beta decay. There are other examples you could look at too, with other elements or even with a positron involved instead. So besides that electron coming out, it turns out there's another thing, a new fundamental particle that takes part in this whole process, which is called a neutrino. There's also antineutrinos that are just like anti-electrons, you can have antineutrinos. So if you're symbolically write out this process, you start out with your element, in this case carbon, you end up getting to nitrogen, which is 1 greater proton than you started with. But you also get out this electron and, in this case, an antineutrino. So that mu is a symbol for neutrino. Finally, gamma decay is a little bit different than the other ones in that you're not actually changing the nucleons, right? You're not changing a neutron to a proton or a proton to a neutron. You're actually going from an excited state of a nucleus to a less excited state. Very similar to when we had like an excited state of a hydrogen atom, right? Like the electron could have absorbed some energy somehow and jumped up to an excited state. So from that ground state went up to whatever n equals 3, 4, 5, something like that. And if it's in that state, it will spontaneously drop back down and you'll emit a photon. Right? That was for a hydrogen atom. Here, a very similar thing happens. Somehow this nucleus gets excited, so it's in this higher energetic state, and spontaneously that state will want to drop back down to this ground state. But to do that, you have to emit energy, and you emit it in the form of photons, very high energy photons, gamma rays. And we can write this symbolically, just writing the element goes to the same element plus a gamma ray. So here we're indicating that the original element, not just the element, sorry, the atomic nucleus, we write a little star on that to indicate that it's an excited state of that nucleus, and then it goes to an unexcited state. But it's not always the case that people write that little star. You see this representation where a nucleus goes to itself plus a gamma ray. It was an excited nucleus, that's kind of implicit. And that's gamma decay. And just to give you some examples of these decays, right, we saw the illustration for alpha decay was actually this top one. It's uranium going to thorium, plus the helium nuclei, the alpha particle. Plutonium can actually go to uranium via alpha decay. And this is kind of examples of like, you don't always write the atomic number on there, right? In this second equation, none of the atomic numbers are there, but uranium is 92. Then we have some examples of beta decay. So like aluminum can go to magnesium. This is actually an example of maybe what you call an anti-beta decay or a beta plus decay, because we're getting out a positron. So that's an electron, but it's plus 1. Meaning there's a positively charged electron, it's an anti-electron or positron. In that case, the proton actually converts to a neutron. So we go to a lower element, aluminum to magnesium. But we still get out that beta particle, in this case positron, plus a neutrino, regular neutrino. You also got thorium going to polonium? I'm not even sure what that is. This is a standard beta decay. You get an electron out and an antineutrino. And finally, some gamma decays, strontium, an excited state, still strontium, but now not excited, plus a gamma ray. And this one, we didn't indicate the excited state in the standard way. I think this is actually a very interesting isotope, technium or something like that. It's going to come up later when we look at medical applications, where it's used in a lot of places to do diagnostic testing, medical diagnostics. So that 99M, well 99 is the mass number, but M there is actually indicating this is a metastable excited state of that element. And so it goes from that to its regular state, and we get a gamma ray out. Something I should really note is that in these decays and nuclear processes in general, you will get out some form of energy from this decay, from the other things you're going to look at, like fusion, fission. And the way you actually indicate that energy is different. People will indicate it differently. The book actually writes these equations, and it writes the energy in the equation as plus Q. I don't think that that's necessarily a good way to do it, but it is important to note that there is energy being released in these processes. Generally, that energy takes the form of kinetic energy of the rays that are being released. So like the kinetic energy of the helium nuclei that's being released here, or the kinetic energy of the electron or the positron, or just the energy of the gamma ray itself here. So now that we know about some of the different decays, it's just kind of interesting to look at some unstable nuclei and just the processes they can go through. So if you start out with uranium, you can go through all these different steps in order to finally get to a stable nucleus. In this case, we start out with uranium-238. Eventually, we're going to get to lead-206. And in these diagrams, where we're looking at the atomic number versus the number of neutrons, so Z versus N, and we just indicate the kind of decays with these arrows. So the orange is the alpha decay, the green is the beta decay, and these are all beta minus decays. They're all electrons coming out, and that's from neutrons converted to protons. But yeah, you can see uranium will go to thorium. Thorium can actually go back to uranium and then to thorium again, and then hard to read that one, maybe radon. So you go through a alpha decay, then you go through a beta decay, and then you go through a bunch of alpha decays, and then another beta decay to get to bismuth, which is an interesting one because it can actually decay in both ways. It could go alpha decay or it could go beta decay. But eventually you get down to lead, an isotope of lead, lead-206. Another example is neptunium-237. And it just goes through this decay series. You go alpha decay, beta decay, alpha, alpha, beta, alpha, 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 beta, alpha, beta. All these processes eventually end up with a stable bismuth nucleus, bismuth 209. This can take quite a long time though, right? You can see the numbers on there are the half-lives. So the half-life of neptunium is like 10 to the 6th years. Decay could take quite a while, but and then other ones are like 10 days, 32 milliseconds. It's just an interesting way to look at the decay of some of these elements. One kind of intriguing thing about these decays and learning about these decays is it helps us understand why the Earth is still the way that it is, why the internal temperature of the Earth is still as hot as it is. Because, when the Earth formed, at least the prevailing theory is that it was mostly just molten rock or different elements, but mostly rock of some kind. I don't know if molten is even the right term for rock, but it was a very hot material when it first formed, and it's slowly cooling down. And it turns out that there's radioactive material throughout the Earth, throughout the interior of the Earth, and so that radioactive material is decaying, and those decays are giving off energy, and that energy is heating or adding to the temperature of the interior of the Earth. If we didn't have those things happening, you could estimate roughly what the temperature of the Earth was when it first formed, and say about how long it would take for it to cool down to its present temperature, to what it is now. And supposedly, without radioactive decays, that would have been about 1 billion years. But the Earth's been around for like 4.5 billion years. Right? So decays, radioactive decays within the Earth help us understand why the Earth is still as warm as it is. So we talked about spontaneous radioactive decay, but there are other nuclear processes that occur, and one of them is sort of forcing nuclei to break apart, and that's what we call fission. The general sort of process shown on the left there is you have this nucleus, target nucleus, or like the parent nucleus, and a neutron comes and smacks it, right? Breaks it apart. The result of that is we get these fission products, or these fragments, or these daughter nuclei, and you usually get 1, 2, 3, some number of neutrons as well, just free neutrons out of there. Also shown here is the fission of uranium-235. We'll talk bit more about this in-between step in a second, but eventually you end up with krypton and I'm not even sure what VA is, right? But these two fragments and then 3 neutrons as well. Like I said, these processes release energy, and the energy that's being released here is pretty much all the kinetic energy of the neutrons, or all that goes into the kinetic energy of the neutrons. This is just a little bit more detail about a particular example of fission that we've utilized quite a lot in different areas, the fission of uranium-235. So, if you're interested in more details of those process and the kinds of products or the fragments that you get out of this fission, these are all the main ones, and this is just a graph of the yield, or like kind of the most likely fragments that you get, and the most likely ones tend to be around atomic mass number 95 and 237. This graph, the percent yield is a logarithmic scale, so these ones up here are 10, 100, 1,000-ish times more likely than this dip down here, which is around 118. Right? That 118 would be almost like splitting uranium in half. Very unlikely that that happens. There's usually more if it goes into one fragment than in the other. And you also see 2 neutrons come out for that one, 3, 3, 2, 3, so a few neutrons come out. And they take away most of the excess energy. We're not going to get really into the details to understand the process of fission. That's just beyond this course. But you can get a little bit of an idea of what's going on here at least, or how we model this process. And that model is known as the liquid drop model. So in fission, that's a neutron that's kind of impacting a nucleus, and through that process, the nucleus ends up fragmenting, breaking into pieces, so you have a couple of large pieces and then a number of neutrons. So this liquid drop model looks at it as like the neutron gets absorbed by the nucleus, and that ends up putting the nucleus into this excited state. And you can kind of think of it as like a drop that just got like hit by something, and so it vibrates. If it is vibrating enough and for long enough, then that vibration can end up kind of pulling the drop into 2 different chunks. And if it has strong enough of a vibration, then that connection gets so small that it eventually snaps. Shown here in 2 different ways, but the neutron comes in, gets absorbed, you get this excited nucleus, and that nucleus is sort of vibrating and eventually can pull itself apart. And in that snapping, you get the 2 big fragments, and then you also get these neutrons created by the energy of that sort of snap. So one way of thinking about that fission is you forming this temporarily excited state of the nuclei, and that excited state is vibrating and sort of vibrates itself apart. So if you've heard of nuclear fission, then probably heard of it in the context of what's known as a chain reaction, or a nuclear reactor, or even a nuclear bomb. It's called a chain reaction because one fission event can trigger multiple other events, and then those other fission events can trigger more fission events, and we get this picture on the left like where one additional neutron comes in and fragments a single nucleus, right? But there's 3 neutrons that come out of that fission process, and some of those neutrons can run into other nuclei, like uranium in this case, other uranium nuclei, which can cause those to go through that fission process, so they'll also split, release more neutrons. Those neutrons can get more uranium nuclei, cause more fission to happen, and you can get this sort of runaway reaction, or this runaway process. Whether or not that's going to happen depends mostly on the concentration of the uranium-235 in that case, right? Or it's the concentration of that, what you call fissile material. And we have a little GIF here where the initial neutron enters from the middle of the bottom of this box, and it runs into one nuclei. That neutron splits one nuclei, which releases fragments, but also high-energy neutrons or fast neutrons. That's the energy being carried away in this process. And those neutrons then can smack other nuclei, break those apart. Those release more neutrons, smack other nuclei, break those apart. So as long as you have enough nuclei that can go through this process that are near enough to each other, then you can start this chain reaction. So that energy that's being released in each of these processes not only can go into causing more fission to happen, you can also kind of absorb that energy and convert it into electrical energy. And then it's complicated actually, because beyond that, the fragments that end up getting formed can also decay, and so they can release more energy too. So it's not quite as simple as just talking about the chain reaction of uranium itself. But the overall idea is that you could use the process of fission and starting a chain reaction in order to release more energy than it took to start, a lot more energy in fact than it takes to start it, and that energy then you can convert to something useful like electrical energy. So we do that with what we call nuclear power plants, and there are a number of different kinds of nuclear reactors. We don't need to go into a lot of the details there, but basically that energy being released in the fission and the results of that fission, the energy released in there, is used to, or is absorbed by some other material, in a lot of cases like water, and that water then gets very, very hot, and from the reactor, pass it through this loop, this primary loop, and allow it to transfer that heat, some of its heat, to this sort of secondary loop. So that's now in the steam generator here. So in that secondary loop, there's also water. It's not in direct contact with the primary loop, but there's like metal, there's something in between them that allows heat to transfer. And so you heat up the water in there, it will turn into steam, and that steam pushes through this pipe towards the turbine. And pretty much you have that steam passing by the turbine, and you can turn the turbine and generate electrical energy by turning a magnet inside a loop of wire, or many loops of wire, or that process from electromagnetism. In practical terms, for that steam to keep turning that turbine, you need a lower pressure area on the other side for the steam to escape, which is why you end up with these big cooling towers for nuclear power plants, because you need to continually cool this steam condenser area in order for the high pressure steam to keep being able to push through. Let's do an example then, having to do with this nuclear power, fission, that good stuff. So you want to calculate the amount of energy produced by the fission of 1 kilogram of uranium-235, given that the average fission reaction of uranium-235 produces 200 mega electron volts. Pretty much we just need to know how many uranium-235 atoms are there in 1 kilogram, and however many atoms there are, multiply that by the average energy released per fission, at 200 mega electron volts. So, to figure out the mass, where the molar mass of uranium-235, 3, is, well, it's going to be pretty close to 235. That's the atomic mass number. It's about 235.04. That's grams per mole. So in 1 kilogram, that's 1,000 grams. We can convert that to moles of uranium-235 via this conversion factor. 1 mole is 235.04 grams. The book actually, I think, has this conversion factor flipped. They get the right answer, but they wrote that backwards. Anyway, that's 4.25 moles of that uranium-235. So how many atoms is that? Well, in 1 mole, there's Avogadro's number of atoms. So 4.25 moles times 6.02, I think 22, but the book just uses 6.02, times 10 to the 23rd atoms per mole. And particularly we're talking about uranium-235, but Avogadro's number doesn't really care. Turns out this is 2.56 times 10 to the 24th atoms. And remember, we're talking about that uranium-235. So how much energy is produced then for that many atoms of uranium-235 if the average energy released per fission, or per uranium nuclei, is 200 mega electron volts? That total energy then is 200 megaelectron volts per, I mean, you don't have to write these units of the uranium-235, but maybe it helps, times however many uranium-235 atoms there are, or nuclei. So this looks like 5.3 times 10 to the 32nd electron volts. Yeah, it's a lot of electron volts. Joules, we can convert to joules. 0.6, about 1.6 times 10 to the minus 19th joules per electron volt. So this turns out to be 8.21 times 10 to the 13th joules. Because I still have a heck of a lot of joules. So 1 kilogram of uranium-235 going through fission releases 10 to the 13th, almost 10 to the 14th joules. The book points out this is roughly equivalent to like 600,000 gallons of gasoline. But again, that sort of gets at the difference between a chemical process and a nuclear process. Burning gasoline is a chemical process. All you're doing is breaking apart chemical bonds, releasing energy. Nuclear processes, you're breaking nuclei, you're releasing that nuclear energy. It's like 100,000 times greater energy, on that order.